Yeah, thanks for coming to this session. We have a lightning talk, so we're going to cover some things rather quickly. I'll introduce myself. My name's Marten. I'm the product manager for the SQL language area at Databricks and also for all things geospatial. Michael, want to introduce yourself?
Oh yeah, hey everyone, Michael Johns. I'm Geospatial Product Specialist at Databricks, work on our field engineering side and work closely with Kent and team.
All right, we're going to talk about the future. The future could change. I hope it doesn't, but that's what this slide means. Buyer beware. All right, in this talk, we're going to cover three main topics. Kind of an overview of where we're at today, the geospatial lakehouse today. Michael's going to talk through some customer challenges and solutions and successes. And then I'm going to talk about our spatial SQL roadmap, make sure we're all on the same page with where we're at with some of the native capabilities in the platform. All right, first topic, geospatial lakehouse. So yeah, we talk about the lakehouse. We're talking about the unified data lake, data warehouse, full governance and security. The things I want to talk about here, though, are that it's really easy to get started doing spatial analysis with vector data and with mobility and GPS data as well. It's like they opened the doors. It's like they're coming in and, you know, they heard me say vector and they're like, let's get in there. But with Spatial SQL, this is currently in private preview. It's super familiar to anyone who's used PostGIS, any relational database with spatial support. So we're bringing all that into Databricks SQL. So I imagine there's probably folks in this room who've tried the preview and have evaluated it. With Spatial SQL, you get a large set of common spatial expressions, and then with our more recent runtimes, support for geometry and geography data types, more on that front. So familiar, the lakehouse, we also consider this kind of the set of capabilities really flexible, really fast. So flexibility, of course you can use SQL, and I imagine most folks here are probably thinking more predominantly if they're using Databricks SQL, they use SQL. But we also have Python and Scala APIs available for all of our spatial expressions. When using H3, the global grid indexing system with built-in expressions in Databricks, this is also, again, we kind of think of it as like a flexible way of working with any type of vector data, but also you can combine it with raster data and do some combined analysis. H3 is great because it really scales well, and Databricks is perfect for scaling that kind of data which is stored as integers. So we have vector analysis, kind of easy to get started with. We have mobility, GPS type data, easy to work with H3. And then if you want to get into more advanced analysis, raster analysis, do it yourself, build your own types of applications, there's a pathway for all of these as well. So this is where I would say the platform really is flexible. And the flexibility comes from the ability to work with the whole ecosystem of really common spatial libraries, right? So whether we're talking about GeoPandas, Sedona, and other tools, these are really common for anyone using Databricks or who has been doing spatial work on the platform for some time. I also want to call out, though, with Databricks apps, you can now build your own sort of purpose-built applications using Streamlit, Dash, other developer application frameworks. This is really something that's come to the platform, I think, in like the last 6 months or so. And there's lots of really good examples that have been built. And I know there's probably another session or two which is focused on building apps. That's something worth checking out. We've got lots of integrations with partners. So if you're working with any of the kind of big spatial partners and spatial vendors out there, know that we are too, and continuing to build new integrations on that front. And then the last thing I just want to mention, you can't really do your analysis without your data and authoritative data to augment and enrich with. So the Databricks Marketplace is a great place because we've got Overture Maps data sets now. We've got AccuWeather, lots of authoritative data sets in there. Encourage you to use it because it's all instant access, easy to use right away. So we've got sort of the full spectrum of use cases supported on the platform. Let's talk about geospatial data types. So this is one of these common questions that we always receive from customers. How do I store my vector geospatial data? Do I work with well-known text? Do I store it as binary? What's the column type, et cetera? Now with Databricks Runtime 16.4 in private preview, we support geometry and geography data types. This is an exciting moment for us. We've been, yeah, go ahead. Yeah, why not? I mean, it's the end of the day, get the blood flowing, right? Like, this has been a long time in the making. I would say, how did we get here, right? So this is really built on the foundation of the Parquet and Iceberg communities earlier this year ratifying the specs to store geometry and geography within those formats. And just yesterday, the Delta RFC was published, so you can see that. And I think my main point here is that there's going to be full interoperability between all these formats, so there's no stress there. There's not some hidden secret or difference between these. And the Databricks team has been a part of these communities and contributing as well. So really excited about this on the storage front, complete interoperability. But it's not just storage. We also have the Apache Spark community has approved support for geospatial data types. And this really standardizes how Spark platforms can work with geospatial data. And really, I think the point here is around between the table formats, between the engine side, you're now using the same type across all these. So it makes it really easy to sort of work with data, makes your workloads portable, all the benefits of being a part of these open systems. Okay. I think the last slide I wanted to cover here on sort of like the current state of things, with geometry and geography types now supported in Databricks Runtime 16.4 in the preview, we've also made some advances to support faster spatial joins. So of course, when we talk about spatial SQL, there's expressions, the types, but really we have a big focus on making sure that we have world-class performance for executing spatial joins and spatial queries. In the preview, there's some known limitations. Maybe this is too much detail to share in this session, but hey, we're here. But we only support SD intersects. It works with moderately sized data. And if you're working with sort of larger data, larger than, say, 10 megabytes on one side of the join, up to 2 gigabytes, you can enforce a broadcast spatial join by using a hint. So what am I getting at here? We're working on accelerating spatial joins in the platform. Right now, we have customers who are testing these joins and working through their workloads with these capabilities. And yeah, sometimes they say, hey, I have a use case where the performance isn't quite what I would expect, given their existing sort of stack. And then other times, we have customers who've shared anecdotes where they're like, hey, this is 5 times faster than my existing solution. So we know we're on the right track. And at this point, I'm just saying, I can't wait for everyone to test it, provide feedback, but also see for yourself. We have a number of other kind of internal milestones that I'll talk about a little bit later. But this is the current state of the union, right? With that, I think I'll turn it over to Michael. He can talk through some of the customer challenges.
Yeah, so this is a lightning talk, so lower your expectations on how far we go with this. I want to touch the outlines, though, of a couple of challenges and solutions that seem interesting to what we generally bump into with customers. The first one is around tessellating of large area polygons. So if you're using H3, if you've used that at all, used it on Databricks, one of the challenges is just customers try to rationalize, how do I handle large area polygons? A lot of times customers will go to H3 Compact. Databricks has a built-in expression for that. Want to make sure you know about that. But also there's custom tessellation compaction patterns that you can also use. So the ability to take advantage of another one of our expressions that may not be as well known as H3 tessellate as WKB. If you look at the bottom of this slide, you'll see 3 columns where normally if you do like a cover as or a polyfill operation, you end up with 1 column, which is the cell IDs that cover that geometry. Tessellate as WKB takes that further and adds additional information. It describes what of the cell ID is core to the geometry when you cover it, and it also goes on and does a chipping operation that at the boundary does an actual ST intersects to determine the actual WKB chip. When you put all that information together, you have 3 fields of information that become powerful for applications like a custom compaction. There's many others, of course. To make that a little more real, on the right side of the slide, you'll see just a quick example. So let's assume that we already have data that has gone through Tessellate as WKB at resolution 5, okay? And so if we want to do a custom compaction, we could say, let's filter that on core equals true. Let's say, let's keep all of the resolution 5 as part of the final result because they're core to the actual tessellation. And let's union that with another resolution of our choice, in this case 9. So we're able to say, let's union with filter on core equals false. So we drop, we basically keep the 5 cell ID, but go ahead and do a tessellating operation on the WKB that we have at the boundary of that initial phase. And then we have at the end of that a 5 and 9 custom compaction. Obviously, I can't go into that very far. But that's a good pattern just to be familiar with that Tessellate as WKB helps you in that situation. Now, at the end of that process, if you don't want to maintain the chips for whatever reason, you can obviously just drop those, and now you have just cell IDs again, but you have a custom compaction. So I wish I could say more about that. Another common one, Kent obviously just talked about this a bit, so I just want to kind of make it real with an example, is joining spatial data, right? So how can you do that using these new features? To do that, I'm going to flip over to a notebook, and I actually have time. They gave us a couple more minutes, so I'm going to go ahead and run this, which is always dangerous live, right? So I'm going to hit run on this notebook. This is running on a serverless cluster in Databricks. It's using our built-in functionality. And this is an example of a spatial join that uses Overture Maps data. So as we scroll through, and this may take a second to run, but as we scroll through, we have our point data, our places in the Overture Maps data set. Now, like Ken said, this is really what we have out of the box right now is one side of the join has to be moderately sized data. So we're kind of following that spirit. Obviously, you could go to any scale with Databricks in different ways, but for this example, we're going to keep it at moderate scale. So we have just 850,000 points in the state of Florida. You can see that it's using, if you can see the screen well, I'm not sure. You can see that it's using our built-in geometry data. So we have this geometry column. It didn't have to be called geometry. I just happened to call it geometry. And so we have this column. We're just calling as text so we can see the WKT output. So we can look at that now. But we're using our built-in geometry for the point data. And then we have the building data, 7 million buildings that we're going to do in this point and polygon join. Again, using our built-in geometry, and you can see the polygons below, and of course all the other field data that's available to that table. So we come down, and we want to do our point and polygon join. And so, Kent described some of this, so this is just a kind of a real example of how to do it. When you look at ST intersects, the predicate we're going to call, we're basically just saying the polygon geometry and the point geometry is what we're using as the parameters to basically the join condition. And we're adding this broadcast hint at the top to say, I want to go ahead and push up to 2 gigs if the data will fit. Go ahead and do that as a broadcast join, which is the most efficient way to do this. So let's see how fast that ran. So it ran in under 15 seconds. So that, that was running while we were talking. But that point and polygon at sort of that scale, 15 seconds, and that produced 300,000 results of matches on points in the buildings. In some way, they intersect the buildings. Now, we could go further. I don't have time to get into it. But, we could look deeper at the plan, and you'll see that, we want this photon broadcast spatial join to be what's used as what the planner came up with. So you can kind of check your work with explain on your query just to make sure things are actually doing what you think. So let me go back now, and this just kind of summarizes what we just went through, just in case something crashed or something on the internet. But two more quick examples. I want to highlight DoorDash as one example. DoorDash wanted to improve their routing services. So I think probably all of us have used DoorDash at some point in our lives. You have dashers, you have customers, and really what DoorDash was realizing was they were doing a lot of on-the-fly calculations. And so when it came time to order being placed, they were having to figure out then and there to calculate an estimated time of arrival, and that was getting expensive as you think of all the concurrent operations they have going on. So they said, let's take a step back and let's do this maybe in a way that helps us out on Databricks. So they used our H3 APIs, and then they were able to take all of their serviceable areas and turn that into cell IDs for the point data that goes with the locations. And then they added to that open source routing machine, and were able to pre-compute an adjacency matrix for what ends up being 6 billion cell-to-cell locations. So they did a pre-computation at that scale on all data, used open OSRM to help them with the routing kind of calculations, and they were able to run OSRM on Databricks, which is interesting because you actually don't have to make as many kind of web calls if you're running it outside of Databricks. They were able to kind of be efficient in that side. When it's all said and done, they were able to take those pre-computed results, cache them, and then get a 10x performance. So instead of having to trade off timeliness or high performance or accuracy, they were able to really get the best of both worlds in a way that's really satisfied this use case. There's a blog on this. These are in the slides, of course, so you'll be able to look at that more if you want. A second quick example and a final example for me involves natural disaster mitigation. So Excel Energy does a number of different things. One of the things they do is wildfire mitigation, if I can say it. They've invested $500 million since 2020 in this initiative. This is a very crucial initiative to their business. And so they wanted to really take this further with Databricks. They were able to use our private preview functionality with Spatial SQL, combine that with H3 indexing, and they were able to transform in real-time weather information into lakehouse-ready data. So from that really good data engineering, they were able to then build, and bring on their ML models, and then take that further with some generative AI initiatives that are coming online now. So all of that together is at terabyte scale of data for the weather data. And they were able to achieve 3x better coverage of their data with this process, 4 times better accuracy, and 64 times faster processing. So a really good success all around for Excel and their partner Newsot, which is now part of Lovelytics, if I didn't mention that before. So that's my section on challenges. Let me pass it on to Kent.
Thanks, Michael.
Yep.
All right. I love those success stories. If anyone wants to join forces and have their own success story published, reach out to me. Let's just talk a little bit about the Spatial SQL roadmap as we get towards the end of the session. So I mentioned earlier, for us on the Spatial SQL side, we're focused on 3 tracks. The actual engine part, which is the expressions, the data type part, which is like the storage, and the performance side of things. The thing I want to convey here is on the engine side, we're focused on complete photonization of all of our expressions. Our testing shows that the photon side of things is going to make spatial queries run as fast as possible. And then we're still looking for more feedback from customers around expressions that aren't supported. On the data type side, now we support geometry and geography. These are based on the specs, as we talked about. In the Parquet and Iceberg specs that you may have already seen, they support 1 SRID or 1 coordinate reference system per column. So that manifests itself in Databricks as just supplying an SRID. So when you go ahead and create a column, you might say geometry 4326, and it's all pretty standard at that point. The types allow us to store statistics that are bounding box statistics, so really useful for spatial queries, which is great. And then on the performance side of things, so although I mentioned in preview we support ST-intersects, and there's some limitations around scale of data, we definitely plan to remove all these limitations or address them as soon as possible, most of which will happen in the public preview. So support for all the common spatial predicates, ST contains, and so forth. And then also sort of a keen eye towards optimizations, where we can rewrite queries on behalf of customers so they don't need to, and apply rules that we can within the query planner. This is the type of stuff that our team is focused on to make sure we deliver the best performance. In the end, we won't just have a broadcast spatial join, we'll actually have a shuffle spatial join to address really large-scale data. So just to wrap up the timeline, which I imagine most folks want to know about, the Spatial SQL private preview is now over. There's no more enrollment into this preview, and we're planning to go public preview with the very next release. So for Databricks Runtime 17.1, that's in July. And for DB SQL, just given our rollout schedule, that would fully roll out by the middle of August at this point. One thing to note, in Databricks Runtime 17.0, so for those of you who are using the private preview right now or are using H3, you're no longer required to have Photon enabled on a classic cluster. So all of these expressions are available outside of Photon. So just to make note of that. And then, of course, I'll just call out, we're always looking for feedback. So I say here, as we move towards GA, it's really important for us to get validation from all of you who end up using the public preview and have used the private preview up to this point to make sure your use cases are supported and as performant as you would expect. The last thing I'll say about Spatial SQL and working in Databricks, 100% you want to use the types. No more storing data as well-known text or well-known binary unless it's absolutely necessary for some existing application. But you want to store data as types and leverage the built-in spatial expressions for the best performance. Okay, with that, yeah, I mean, this is a huge time. We had an applause mid-session because we talked about geotypes, but hang on. Hold the next applause. I just want to say there's a few other talks. This is the audience here you guys probably care about. Later today, that's why people are leaving for no other reason, the 410 session. And then Wednesday and Thursday, there's a few other talks as well that might be of interest. Encourage you guys to go there. If you can, please fill out the survey. It helps us make better content. I know this was a quick lightning talk. Hopefully we did all right. But please fill it out, and we'll do better next year. And continue your learning journey. That's it. Thank you so much for coming.